Assalamu alaikum. In this video I will be describing the method to graphically draw the 4-bar quick return mechanism. So this is article 3.5 from the book of Design of Machinery by R.L. Norton, 6th edition, page number 119. So in this article I will briefly be reading some important descriptions as mentioned here, so that if there is some important point that I will be explaining. So here actually in the quick return mechanism, first is the 4-bar quick return mechanism. So here the author states that the linkage synthesized in example 3-1 in the previous video which I have explained is perhaps the simplest example of a 4-bar linkage design problem. So I have described the procedure for figure 3-4 in the previous video, and it is a crank rocker that gives two positions of the rocker with equal time for the forward and return stroke. So it was already stated in the video that because that gave the equal throw in the forward and the reverse stroke between the two extreme positions of the rocker. So this is called the non-quick return linkage, and it is a special case for the more general quick return case. So that means quick return mechanism is the general case and non-quick return is the special case for which the throw is equally transverse between the two extremes in the forward and in the reverse stroke or in the back stroke. So that states that the reason for its non-quick return state is the positioning of the crank center O2, and O2 is actually the crank grounded revolute joint is on the chord A1 B2 extended, which I have stated in the video that the extremities of the rocker link, the line connecting the extremities of the rocker link is actually the chord of the throw of the rocker or the oscillating curve of the rocker. So this result in an equal angles of 180 degrees being swept out by the crank as it drives the rocker from one extreme or toggle positions to the other. If the crank is rotating at constant angular velocity, as it will tend to when motor driven, then each 180 degrees sweep forward and back will take the same time interval. So it has been stated in the video that the crank will be moving with constant angular velocity and the rocker will be moving will also be moving with the constant angular velocity in the forward and back stroke. So now the author states that if the crank center O2 is located off the chord B1 B2 extended, means the line connecting the extremities of the rocker. So if the crank grounded revolute is not located on that line, so then as shown in the figure 3-1b, figure 3-1b, I can show it here. Let us see the figure 3 dash. Here this is figure 3-1b. as we can observe that this crank grounded revolute is not on the line connecting the extremities. This D1 and D2 are the extremities of this rocker link. So O2 is offset because that line will be here and the point O2 is below that line, so that is not located on the line extended between the extremities of the rocker. So in this way now, so here that and in figure 3-12, which has already been explained here, sorry, this is figure 3-12. So as we can observe here that these are B1 and B2 are the two extremes of the rocker. So the line will be here in this path. So this O2 crank grounded revolute is not on that line, so this will be giving unequal times between these two extremes in the forward and in the reverse stroke. So there may be in the forward stroke there will be taking more time and the rocker will be moving slowly from B1 to B2, and while reversing from B2 to B1 the rocker will be fastly or quickly returning, while the crank will be moving with constant angular velocity while rotating 360 degree. So that has been stated here. Now it states that unequal angles will give unequal time when the crank rotates at constant angular velocity. So these angles are labeled as alpha and beta in the figure 3-12. So we can observe here this is angle alpha and beta, and as we can observe that this is the crank circle. So angle alpha, as we can observe, is smaller, and beta, angle beta is from this line to this line, because this is straight line, this is 180 degree. So that means this angle is additional covered by an angle beta. So this is the forward stroke and this is the quick return stroke. So in this way, that means that the crank will be moving from position when the crank will be moving from position A1 to A2, then the rocker will be moving from extreme 1 B1 to B2, and as more angle is covered greater than 180 degree, so that will be comparatively moving slowly with lesser speed, and when it will be reversing or coming back to A1 position from A2 to A1, so it will be relatively going back faster in this orientation. So in this way, that actually explains the quick return mechanism. So that means that angle beta is actually the angle for the forward stroke and angle alpha is the angle for the return stroke. So here it states that their ratio alpha by beta is called the time ratio, or capital T subscript R, and define the degree of quick return of the linkage. So that means that the degree of quick return, if beta is smaller, means as much smaller, that will necessarily be greater than alpha, but as much smaller, then the degree of quick return will be increased, and if beta will be increased, if beta will be increased, then time ratio will be decreased. So in this way, this actually defines the time ratio, that that actually define the degree of the quick return. So that note that the quick return term is arbitrarily used to describe this kind of linkage. So if the crank is rotated in the opposite direction, it will be the quick forward stroke. Means if work is done in the forward stroke, in the fast stroke, so that is called the uh, quick forward stroke. So actually the term return means when the uh, output link is not actually performing any useful work. So if in the in the quick stroke it is performing some useful work, so it will be called quick forward stroke. And slow return stroke and quick forward stroke, so these terms can be used. So that state that given a complete linkage, it is a trivial task to estimate the time ratio by measuring or calculating angles alpha and beta. So in this way, so this is the time ratio alpha by beta, and as we can observe, alpha plus beta, their sum is 360 degrees. So time ratio is defined as, if we know that the angle alpha, then beta will be equal to 360 minus alpha. And as we can observe here that we will be defining the term delta, which is actually as we can observe that at 180 degree, if the throw in the forward or in the reverse stroke were exactly 180 degrees, then it would give the non-quick return. So that means we can subtract 180 minus alpha or 180 minus beta, so their absolute magnitude will be equal to delta. So this delta will be actually used to synthesize or create the linkage of correct dimension sizes. So the procedure is explained here. So I will be explaining the procedure from this diagram briefly. So in a similar manner as previously explained, that we will be assuming some suitable size or dimension for the rocker, so that will be assumed or that will be given, because that is the output. So we will be requiring that the output is already defined or our requirement. So this will be in one position, the rocker will be drawn, and after that we will be placing the protector 0 degree 0 line along for example this position, for example O4 to B1. So O4 is the rocker grounded revolute, so we will be pressing the 0 line along this O4 and B1, and then we will be measuring or the angle subtended at this O4 by this rocker. So its total throw will be defined with the help of protractor. So there will be the 0 degree line, and we will be measuring, for example, as in the non-quick return mechanism, I have assumed the throw to be 100 degrees. So from here 100 degrees will be measured with the help of protractor, and this will be the other extreme of the rocker. So in this way, two extremes of the rocker will be made on the page, will be drawn on the page. And after that, what we will be doing, previously for the case of quick return, what we did, that we simply created this chord B1 and B2 and extended it in the forward orientation. But now what we will be doing, that we will be drawing a random line at any suitable orientation. That line will be passing through this right extreme B1 from of the rocker. So after that, what we will be doing, that we will be defining a line parallel through B2. That line will be parallel to this initial line that has been drawn, this right extreme of the rocker. So another line will be drawn parallel through, and with that parallel line we will be measuring the angle this delta angle by we will be placing the protractor here, and with that parallel line we will be measuring this delta, and after that at delta orientation we will be describing or specifying this line at that angle, and because this line is not parallel to this line, so that will be intersecting, and the intersection will be named as or termed as the O2, and which is actually the crank grounded revolute, and in this way O2 O4 will be the grounded link, which is actually denoted by the scalar letter small letter b, scalar length d. So that will be the d length as O2 to A4 is shown in figure B1, and after that what we will be doing, that we will be specifying the sizes of the connecting rod and the crank. So how they will be specifying here in the 7th clause of procedure, the author has mentioned that find the lengths of the crank and the coupler by measuring O2 B1, means from O2 B1 and O2 B2. So we will be measuring with the help of linear scale from O2 B2 and O2 B1. So after that we will be writing these equations, means for example coupler if we denote it by small letter b and crank is denoted by usually let small letter a, so b plus a will be equal to O2 b1, that will be measured, and b minus 1 will be, because actually when in this position we can observe that from A2 to B2 is actually the total length of the connecting rod, and because the in this case as we can observe here in this in which the author has drawn the physical links drawing, that from A2 to B2 is actually the length of the connecting rod, and the crank is this connecting rod is actually overlapping or hiding the crank. So crank is actually underneath this A to B2 link, which is actually the connecting rod, and this is the overlapped position, and this is the extended position where A1 B1 here A1 B1 is actually the connecting rod. So in this way the distance from O2 to B2 will be equal to B minus A. So the distance because A2 to B2 is actually the length of the connecting rod, and from O2 to A2 is actually the length of the crank. So the distance from O2 to B2 will be equal to B minus A, and in a similar manner from O2 to B1 the distance will be B plus A, because this distance is A and from A1 to B1 is actually B. So what we will be doing, that we will be solving these equations simultaneously, and after that another method that can be that once this intersection has been obtained, once this intersection has been obtained, we will be measuring this distance from O2 to B1. We will be measuring with the help of linear scale this distance, because this circle will not be will not have been drawn by then. We will only be getting the intersection O2. So we will be measuring the distance from O2 to B1, and we will be placing the compass center at B2, and we will be describing an arc. That arc will be actually intersecting this line B2 B2 O2 extended at A2. So in this way, and now this distance O to A2 will be the length of the crank. So we will be we will be opening the compass equal to the radius A2 O2, and at this center we will be describing this circle, and this circle will be intersecting this line O2 B1 at A1. So these are two extremes of the crank. O2 A1 is the extreme of the crank when the rocker is at extreme B1, and the other extreme of the crank is O2 A2 when the rocker is at extreme B2. So the angle from A1 to A2 is actually the forward stroke or angle beta, and this is the reverse return stroke which from A2 to. In this way, that the author has actually sketched the physical links. So in this way the mechanism will be look like when it will be fabricated. So this is the brief procedure, but now I can explain this procedure on MS Word. So as for quick return, non-quick return, I have described this procedure, so I can just copy this complete or necessary sketch on another page. So the we will first of all be selecting these diagrams. So what will be the method to select? That we will normally be selecting, for example, this position of the rocker, and after that press Control button from keyboard, and then click on this other extreme of the rocker. Sorry, here if some link is selected, then once again click it to deselect it. So that will be, sorry, deselected. Sorry, once again, actually it is not responding. Once again, click on this link, then press Control button, then for example click on this link, avoid labels area. So click on this link, because no, sorry, this link is not required. So only we will be requiring the extremes of the rocker, because that link D will be defined later. So actually we only require these two extremes and extreme of the rocker. So again we can click on this arc as well. So that has also been selected, and furthermore if we want, we can copy this point, center point of the throw as well, just as an optional, and here this line can also be copied. So selected, and now we will be copying, Control plus C, and now we can for example move to some other separate page, fresh page here, for example, near the center we can paste here. As we can observe, now what we can do, we can just move it here like this, as we did already. So here like this. So in this way these extremes have been specified. So after that, what we will be doing, that we will be describing I can also copy the labels. These labels B1, copy, control, and copy, sorry, no, labels will be separately copied, so just copy it and just paste it here. Sorry, once, just copy this label from here, copy, and just paste at suitable location, and now move it here. So this is position B1, and now just again copy and paste it, and then move it to and change it to just B2, and again for example just paste and change it to O4, or that can be copied from there, so that is simple, just change them. This is this is O4. So in this way rocker labels have been completed, and its 100-degree throw is already specified. So just to save time, so after that we will be drawing that random line here. So just assumed line, for example randomly here at any suitable distance here, for example at any suitable location here, like this. So in a similar manner we will be performing the dimensional synthesis once, and after that we will be apply the Grashof law. If the Grashof law is satisfied, then the dimensions that have been specified are all okay. Otherwise we will have to change the size of the rocker, and will have to redraw the linkage until the Grashof law is satisfied. So this is actually the random orientation of the line. So as this is the reference line, just change it as for example in some dashed pattern while you are drawing on hard paper, in drawing sheet or A4 size papers. So make them always in the center line format or in the dashed pattern, because they are just the reference lines and they are not actually the physical links practically. So this is the first random line that is passing through B1. So after that we will be drawing a line parallel to this line. So just for example I can just copy it and just I can move it here. So in this way, that is quite simple, that I can just pass from this extreme B2. So in this way, or you can use up or down arrows for exactly location. So these two lines are parallel, and after that what we will be doing, that we will be placing the protractor here, move it, and place the this zero line like this here at center B2, like this as 0 degree line is here. 0 and 180 degree line is actually hiding this line which is parallel to the randomly line drawn through extreme of the rocker B1. So now as we can observe the throw for the rocker that we can actually specify here. For example, in a similar manner I can insert here if the delta symbol is available somewhere. I actually search out here. If it is available easily, then I can add. Otherwise I will just so here this is I can say this is the delta symbol. So delta here I can define, for example, the delta is somewhat I can say 20 degrees sufficient, for example. So 20 degree delta has been assumed. So draw this line at 20 degree from here. This is the 20 degree position. So now extend it here like this, in this way. So as we can observe, this angle is actually delta. That can I can mention it here. Go into the insert and go into the shapes, and again, like for example, just draw an arc here like this. So this is the delta symbol. So for example, use text box here, and then you can insert the delta symbol here like this, and again shape format, shape fill, no fill, shape outline, no outline. So in this way this angle delta has been defined. Or I can further also mention here that delta is actually 20 degrees. So like this. So again change it to, so in this way delta that has been defined. And after that move this protector out. Also you can convert this into a dashed pattern, because that is just a reference line. So this means that just copy some label here, for example this label, copy and paste here, and then move it here to define. This is actually O2, or the crank grounded revolute. In this way, crank grounded revolute that has been specified, or its better location. For example, just copy this smaller circle here and move it to here. So in this way point O2 has been specified, and after that we can either use that formula a plus b, this is O2 B2 we can measure, and O2 B1 that can be measured, and then we can solve these two equations simultaneously. Or what we can do here, that with the help of this linear scale, let us measure this measure O2 B1, O2 B1 for example like this. O to B1, as we can observe that here is 14. O to B1 is actually 14. So here at this stage I will be explaining that the seventh clause that actually states that find the length of the crank and coupler by measuring O2 B1 and O2 B2 and simultaneously solving. So as already explained that we can either solve these two set of equations to determine the length of the coupler and the crank, or the other procedure that the author has mentioned, that you can construct the crank length by swinging an arc centered at O2 from B1 to cut line O2 B2 extended. So that actually describes in this statement or in this sentence that what we will be doing, that the other procedure to determine the this crank circle, is that, or the crank length is that, what we will be doing, that we will be taking the center, this O2 will be the center of the compass, and then we will be opening the compass radius equal to the length O2 B1, as it has mentioned here that the center will be O2 and from B1. So the radius of the arc or the compass radius will be O2 B1, and we will be describing a circle or an arc that will be equal to the radius O2 B1, and that will intersect the line O2 B2 here. If we extend this line, so that will make intersection here. So we will be obtaining this B2 B1 dash line that the author has stated, that label that intersection as B1 dash, and the line B2 B1 dash is twice the crank length. So this line, as the author has mentioned here, that is actually 2A2 O2A2. So this is actually, this is the length of the crank, which actually later will be specified, but this distance is actually double of this distance. So we will be taking the half of this distance, we will be measuring this total distance. This is actually double, so that means its center point will be somewhat here, so we will measuring its half distance, and then we will be taking the this compass center at this point O2, and we will be describing this crank circle, so that will be intersecting at two position A1 and A2, and if this way these will be the two extremes of the crank. This extreme of the crank O2 A1 will be when that rocker will be at extreme B1, and the other extreme of the crank will be when rocker will be at the other extreme B2. So in this way, so now that I can apply the same method, that first of all measure the this length O2 B1 O2 B1. So as we can observe here, that this length is here somewhat here as well, 13.567 13.6 somewhat. So the radius is 13.6 centimeter here, 13.5 and 13.6 approximately, or we can say 13.7 for example. So this is about 13.6 or 13.7. so as this is the graphical work, so there may be slight variations in observation, so that doesn't make an issue. So how that arc can be drawn, that with the help of the protractor. So I can make it here, no issue, just that will give us an exercise. So here like this, maintaining this center and open this protractor equal to this much radius. So I can resize it. Again, here. So now resize. Here again a bit resize. And here, as now we can observe that this extreme B1, that the center of the protector is at O2, and this zero line or the boundary of this protector is at B1. So in this way, so as we can observe here, that this point will be the B1 dash. So just go to insert and shapes area, and similarly describe this arc here, but now no needs to describe, or we can just simply draw indicator, just a simple line here at this location, just here at this location. So now we can move this this protector out. Like this. So as we can observe here that sorry, I can copy, for example, this label and then paste it here, that this is B1 dash. So now, for example, measure its length using this linear scale. This linear scale here very carefully. So here we can observe, sorry, here we can observe, if we can zoom in, so as we can observe here that maintain move this angle delta out. So now carefully observe that here it is somewhat, we can say 7 centimeter. 7 centimeter is actually B2 B1 dash, as it is mentioned here, B2 B1 dash, twice the crank length. So that means about 3.5 yeah, means here this will be the crank length 3.5. so that means move this scale here, and here it is 3.5. so just go into the shapes area and this circle like this, and or we can use just that protector, that will make work easier. Like this. So here like this. Now we can resize it 3.5 exactly like this. Use up and down arrows very carefully. here. So here the boundary of the product is at 3.5. so practically we can use just compass radius equal to 3.5 and describe a circle. So now for example you can use this shapes area like this and just resize it. Here like this. You can use shape fill to no fill. So in this way. So now the protector can be moved out. So crank two positions now can be drawn. Just make this circle in some dashed pattern because it is just a reference circle. So here like this. So now use labels. This is actually A1 as shown in the book. This is A1 and this is A2. So just copy this label and just copy this label and paste it here and change it here, that this will be A2. So now angle alpha and beta can also be defined, but we will be describing actually the so this is angle beta, this is the forward stroke, and this is the angle alpha that can also be drawn here using just arc command here like this. So angle alpha and beta that can be measured with the help of protector, but now mention the ground link O2O4. So draw the line here. So this line is actually the grounded link, so you can make it a bit bold. And in a similar manner, I can just approximate the here like this. Sorry, this is the ground link, and So these two positions of the quick return 4-bar mechanism have been drawn. We can also, for example, color them. Just go into the shape format, for example, shape fill into some suitable colors, for example this, and similar manner this crank and this ground we can different, or we can change it some black color. So the other position, so in this way other sizes shapes of the links can also be shaded, but now I will be mentioning or specifying the sizes that A is equal to 3.5 and B as that can be measured here using this linear scale. We can measure the B directly, that between this line and here we can zoom that, sorry, not that, very carefully, that up to A2 to B2 is actually the length of the connecting rod. So very carefully that the distance is 10.11 12 13 10.11 12 13. So that is equal to 10.3 centimeter. So the length of the connecting rod actually that comes out to be 10.3 centimeter approximately. Here A is equal to, and now the length of D, that just move this shade out and this link. So I had just shown, now I am removing these shades, so actually that make no sense. So now measure this here so as we can observe here that this distance is approximately equal to 9.12 and 9.3 centimeter approximately. So D is equal to 9.3 centimeter. So now apply the Grashof law. So the smallest also mention here the C that was actually 5 centimeter. So now the largest link is actually, smallest link is 3.5 plus the largest link here is 10.3. so this comes out to be 13.8, I think 13.8 centimeter, 13.8 centimeter. And whereas P plus Q are the other two links, so one is, for example, rocker, that is 5, and plus D is equal to 9.3, and this comes out to be 14.3 centimeter. So when, according to hence Grashof law has been satisfied, because this is S plus L is less than P plus Q. So the sum of the length of the smallest link and the largest link is equal is less than the lengths of the other two links P plus Q. So and this Grashof law has been satisfied. So that means our analysis, our synthesis is all correct. So in this way the synthesis will be done and the links will be fabricated, and now we can move these link sketches out. So this is actually the final diagram that I can show it here in the zoomed orientation. And also if we want, we can show, insert the angle beta, for example here. If we, this is angle beta, so also angle alpha here like this. So just for example copy this label and move it here, and sorry, so this is angle beta, and just this is angle alpha, that can be, sorry, just copy this label or some other label and move it here, and sorry, this cut, and here this is angle alpha. So in this way final diagram has been shown. Now we can also verify the angle alpha and beta values. So use this protector. So as we can observe here, that from here this is 20 degree, so up to here this is 180 degree. So as we can observe that the angle beta is actually about 200 degrees, so whereas this is equal to 160 degrees, because here it is 20 degrees. So from this position of the crank up to this A2 to A1, this line is A1, so this is about 160. So in this way angle alpha and beta have been mentioned, or we can also define here the time ratio. For example, here I can mention the T subscript R time ratio, that is actually equal to, according to the book, that is equal to alpha by beta. That is equal to alpha by beta, and where beta is the forward angle and alpha is the reverse or return angle. So as we can observe that beta is equal to 200 degrees and this alpha is 160 degrees. So in this way time ratio can be defined